In this video, we are going to learn about electron configurations and the information that we can obtain from the group number and the periodic table. So, when it comes to electron configurations, this is related to the Schrödinger equations and all the information that we learned from shells, subshells, and the number of electrons that can be positioned in them. To summarize it, electron configurations are going to illustrate the distribution of electrons in an atom. What is it specifically? Here we are going to know where are our electrons located in the context of the quantized energy level, in other words, the shell, and the subshell or orbital. Okay, so that's what we're doing. Now, we just learned previously that we're going to have different shell numbers. Shell number 1, number 2, number 3, number 4, all the way to number 7. Depending on the shell number, then we also have subshells. Now, we haven't discussed yet how are they actually organized. How do we actually fill them? And as you can see, there is a particular order in which they are filled. There's two ways in which you can know how they're filled. One, you can use the step ladder method, which is what is illustrated in this slide. And as you can see, the orbitals and the shells and the subshells are illustrated here. In the step ladder method, as you're going to go, is to move around kind of like a snake motion. And basically we go, the first one that gets filled is, I'm just going to highlight them as I go along. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5p. As you can see, I'm following the trace, okay, all the way to 6d. So that's all what I'm doing. The other method that we can utilize in order to write electron configurations, and notice that electron configurations are not discussed in the textbook. So please pay close attention to this concept. Now, when it comes to electron configurations, we can also utilize our periodic table in order to determine where the electrons in a particular atom live. What we have to do when it comes to that is that, remember, you can look at the periodic table and please just select the different blocks so we can actually highlight the different areas in the periodic table. So for the purposes of electron configurations, this element right here, which is helium, is going to be now in this corner. Helium is not part of group 2A. It's just that for the purposes of electron configuration, we think, okay, is going to be here, part of the S block, okay? So the first two columns in the periodic table that are going to be part of the S block, the middle, which we have our transition elements that are going to be the D block. Down here where we have the lanthanides and actinides, that's going to be the F block. And over here from 3A to 8A, not including helium, from the 8A, that's going to be our P block. If you see the larger numbers that we have here, those are going to be the period numbers. And remember, there's only 7 periods in the periodic table. 1, 2, 3, 4, 5, 6, 7. Another thing that I wanted to point out is that notice that when it comes to the D block specifically, even though here is where we start with the D block, notice that even though that they are on the fourth that they are lined up with the fourth row, they start at 3D. So this goes 4S, 3D, 4P. So notice that at the D level, we always drop a period. That is just how it was established experimentally. Okay, that is just something that you should keep in mind. Okay, so In a few minutes, I will go through the examples of how we are going to utilize the periodic table in order to determine the electron configuration for a particular element. But I just want to continue gathering other information that the periodic table gives us other than electron configuration. The next thing that I want to discuss is the presence of the group numbers and what are valence electrons, okay? So understand that when we have representative elements, remember, those are the ones that are in group 1A to 8A, they are going to have a specific number of valence electrons, okay? And again, within those groups, those elements are going to share similar chemical properties, okay, due to the number of valence electrons. What are valence electrons? These are going to be the number of electrons that are in the outermost shell, okay, of a particular atom. Now, the group number is going to give you the number of valence electrons for these representative elements. And as you can see, it is summarized in this slide. If you're in group 1A, you have 1 valence electron. 2A, 2 valence electrons. 3A, 3 valence electrons. All the way to 8A, which has 8 valence electrons. Now, you will see that in chemistry, we always have exceptions to the rules, and this is one of the first ones that I'm going to give you. In group 8A, there's an exception. Helium is the only member of 8A that does not have 8 valence electrons. It only has 2, okay? But because those 2 electrons live in the s orbital, then we're going to learn later how that actually gives helium its stability. So understand that this group number with the valence electron works for most atoms. The only exception to the rule is going to be helium, okay? Now, there's a way in which we can illustrate those valence electrons. Understand that it's just by placing dots around the element symbol. And as you can see here, aluminum, which is in group 3A, has 3 valence electrons. So that's why when we illustrate it, it looks like this, Al with the 3 dots. Now, let's actually do some practice problems to understand the whole idea of electron configurations. And as you can see here on problem 5 and 6, I'm not going to do all of these problems. I'm only going to be discussing specifically, let me just highlight them, lithium, sulfur, and iron, okay, which I'm going to give their group number, total number of electrons, valence electrons, and electron configurations utilizing the periodic table that I have on the next slide, okay? Then make sure that you practice all of this. The answer key for the worksheet has been provided to you on Canvas, okay? So let's start working on the problem itself. So I'm just going to write notes around here. I'm going to be writing the particular elements in the bottom. So I have the symbol, and I have lithium, I have sulfur, and I have iron, okay? The next column is the group number, followed by the total number of electrons, followed by the number of valence electrons, followed by the electron configuration. I'm just going to write some lines to just separate these. and gather all the information. So let's get started with lithium, okay? Lithium, which lives right here, is going to be in group 1A. How do I know the total number of electrons of lithium? Well, I look at its atomic number, which is 3. Number of valence electrons, because it lives in group 1A, it will have 1. Now let's go over the electron configuration. So you have to imagine or envision that electron configurations is going to be kind of like a board game, but you're counting all the boxes. So as you can see, lithium, which I'm going to highlight in green, is on box 3. That means that when we're trying to define its electron configuration, we're going to highlight all the boxes preceding lithium. So that means that we're going to highlight helium and we're going to highlight hydrogen, okay? Remember, when it comes to electron configurations, the periodic table is going to be divided into blocks, okay? And I'm just going to utilize other highlight colors to represent the different blocks. So I'm just going to draw here my helium to make it more obvious. Let me just block it out. And just highlight it here, but block it out on the other side. Okay. So as previously mentioned, the first 2 columns that is the S block. This in the middle right here, that is the D block. These guys right here are going to be the P block. The lanthanides and the actinides that are going to be in the F block. Okay? So let's get started with lithium. So when we're writing the electron configuration for a particular element, understand that we're going to always start at the first corner. Okay? So on level 1, okay, which this periodic table doesn't have the periods in the corner, but I'm going to write them in. So this is period 1, 2, 3, 4, 5, 6, 7. So understand that the period number is going to be your shell, and then the blocks are going to be your sub shells. Okay, so on level 1, if I draw a line, as you can see, other than the 2 boxes for hydrogen and helium, there's nothing else. This is level 2, this is level 3, this is level 4. Okay, so for lithium, on level 1, we have 2 boxes on S, okay, the hydrogen and the helium. And then on level 2, on the S block, we only have 1 box to get to helium, okay? So that is the electron configuration for helium. How do I verify my answer? Because if you add the superscripts 2 and 1, that equals the 3 electrons in lithium, okay? How do I verify my valence electrons? I will look at the highest shell number. As you can see, that is 2. And on level 2, I only have 1 electron. That's where this one comes from. Let's move on to sulfur. So I'm just going to erase my highlights in lithium. And I'm going to do sulfur now. So for sulfur that lives here, then we need to highlight everything before it. And we're going to count all the boxes that are preceding sulfur. We're going to go row by row, box by box. Okay, so let's start filling up this information. Sulfur lives in group 6A. Total number of electrons, 16, because of its atomic number. Valence electrons, because it lives in 6A, it has 6 valence electrons. Let's write its electron configuration. Starting at level 1, block S, there's 2 boxes. Level 2, block S, 2 boxes. Then we move across the periodic table. Level 2, P block, 6 boxes. Then we proceed to level 3, neighborhood S, 2 boxes. And then we go level 3, P block, there are 4 boxes, okay? For those of you that may be a little bit like, okay, how did she do that again? Okay, neighborhood. So first level, 2 boxes on the X block, and there's nothing else on level 1. Level 2, 2 boxes. Level 2 on the P block, 6 boxes. Level 3 on the S block, 2 boxes. Level 3 on the P block, 4 boxes. And this is where I stop for sulfur. That's how I came up with that. Okay. Then, as I mentioned before, you can verify your answer. You can say 2 plus 2 plus 6, that's 10, plus 2, that's 12, plus 4, those are the 16 electrons. Those 6 valence electrons, where do they live? Well, I look at my highest shell number. As you can see, I'm highlighting it here in yellow. So as you can see, if I add 2 plus 4, that's where the 6 valence electrons for sulfur comes from. Let's move on to our last example, which is iron. Let me just erase. This work that I have here for sulfur. And let's move on to iron. So let me highlight iron. So iron lives here. Then I'm going to highlight everything that is before iron. All the boxes before it. Okay? Because all of them are going to count for its electron configuration. So, when it comes to iron, group number, as you can see specifically, that is 8B. Total number of electrons in it, 26. Valence electrons, I'm not going to answer yet, because remember that the number before the letter, it must be before the letter A in order for me to say, oh, this is the number of electrons or valence electrons in a particular atom. Because iron lives on a group B, then we cannot assume that is the number before B. Okay, let's write first the electron configuration and then do the number of valence electrons in iron. Okay, so let me rewrite my helium here. So if I highlight as I go, for the electron configuration for iron is going to be 1s2. There's nothing else on level 1. Then I go 2s2. 2p6. 3s2. 3p6. 4s2. And once I get to the D, remember, even though they're in row number 4, here we start 3d1, 3d2, 3d3, all the way here, which is 3d6. Okay, that's the electron configuration for iron. We can verify that we did the correct number of electrons. 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, 18 plus 2, 20 plus 6. Those are the 26. When it comes to the valence electrons, again, because iron is part of the transition metals, we're going to do the same thing that we've done before. We're going to look at the highest period number or shell number that we have. In this case, it's going to be 4s. And there's only 2 electrons. So for iron, there's only 2 valence electrons present. Again, it's because the highest shell number has to be considered and then all the electrons that live there.